All right, so today we are doing 5.3, which is graphs of relations and functions. So looking at the differences there. So our objectives, we're going to use a relations graph to determine its domain and range. So we're going to look at the graph, determine the domain and range, and determine whether it's a function or a relation, right? And then we're going to graph some simple relations and functions. So first up, if we imagine a ball being thrown from the outfield in baseball, can you imagine that? Okay. The height of the ball depends on the length of time it's been in the air. So t, which is what? What's t? A variable for what? For time. T is for time, right? Because we just said time, the length of time, is depends on, or the height of the ball depends on the time. So we're talking about time and height. T is the independent variable. So h is the dependent variable. And what's h stand for? Height. Yes, right? Because it said the height of the ball depends on the length of time. So we're looking at h, height, t, time. All right, so since there are infinite points in this relation, well, what does infinite mean? Non-ending. Okay, so there's infinite points in this relation. Okay, the domain and the range are stated as inequalities. So this is different. Like, look at this domain. That is different than what we've been writing for domains. Okay, but we write it this way when there is an infinite number. How do we know if there's an infinite number? Well, if there is an infinite number, we write an inequality. How do we know if there's an infinite number of them? Not quite. Not because I've written an inequality. What? It never stops? This graph looks like it stops. Okay, so we are writing this in regards to this graph here. Okay, that is a graph measuring the height over time. So this is our height of the baseball over time. So notice it doesn't start at 0, it starts at like 6, right? Okay, no, it's not 5, it's above 5. Okay, or maybe it might even be 6.5 or something, but and then the height increases and then it comes back down to about 6.5. 6.5. So what is happening to the ball?
It's flying.
It's flying. It's being thrown. Okay. Okay. Like when we talk about a soccer ball, it's being kicked. Where is the soccer ball when we kick it?
On the ground.
On the ground. So it starts from 0 and we kick it. Where is this baseball when it's being thrown? In your hand, okay? And typically, like professional baseball is men, right? We have men's professional baseball, and when they throw, do they put their hand low to throw, below their waist, or do they raise their arm up to throw? Up, okay? So the ball, when it's starting its trajectory, it's starting at about 6 or 6.5 feet because someone has their arm raised to throw the ball, okay? So it's not starting at 0. It would, yes. And so this is like maybe just one person or something. So yes, it does depend on how tall the person is, okay? Because my height, my throw would be different than my husband's, okay? Or Hayden's height would be, like from his throw would be different than Brandon's, okay? All right, but there are infinite points. We know there are infinite points because all of these points are connected by this line, okay? So when we have a line, that shows us that there are infinite points. Okay, because we could check the height at time 2.7 seconds and at 2.9 seconds, and we could check it at 3.7 seconds. Okay, we could check the height at any of those times in between there. Okay, so we write them as an inequality in this case. So if we look at the domain is our x or our y? Domain is the x, okay. I wanted to change my colors. Okay, so domain is my x values. So this says it is time such that 0 is less than or equal to our time, which is less than or equal to 3. Where are they getting these 0 and 3 from? Right? Where are they getting this number and this? The graph? Where in the graph?
The t is on the x-axis.
The t is on the x-axis. Yep, so here's my t. Starts at 0. and it goes over to 3. Good, that's exactly it. So we're starting at 0, we're going over to 3, and we can look at any t value in between 0 and 3. So 1, 0.001, okay, 2.7, 2.89 seconds, like whatever it may be. But that is exactly right. That's where we're getting those values for our domain. We know the domain is our x values, so we look at our x axis and see where we start and where we end, and we put those in there. Okay, so then what about for our range? So for our range, we have our h, or our height, such that 6 is less than or equal to our height, which is less than or equal to 20. So what's the range? Represents the y-axis. Okay. Yeah, and it starts at 6. Nice. That's a great way to describe it. The highest point it reaches is 20. Okay, so it could be the lowest point. Sometimes maybe our graph would go down and we would want the lowest point. But yeah, so we have this is our lowest point. So we're looking for our highest and our lowest points to write our range. Okay, so domain is like the left and the right points. The range is the highest and the lowest points when we write that inequality. And this is when our graph is connected. All right, perfect. Then we have a vertical line test. It determines if the graph of a relation is a function. Have you guys ever heard of the vertical line test? No? Okay. So all you're going to do is you're going to imagine placing a ruler, and I will do that on this paper. Otherwise you can't see it in the video. So you just imagine placing a ruler on the graph. If the vertical ruler touches the graph in more than one point, then the relation is not a function. Does this ruler, like do these vertical lines, does it touch the graph in more than one place? No. So then this is a function. Okay, the other thing is you can draw vertical lines. Does it touch the graph, that blue graph, in more than one place? No. So this is a function. That's simply it. Because remember, what was a function? What did we talk about last week? Okay, the x value doesn't have any shared y values, because if it did, okay, if we had an x value that was 1, and let's say 1, 1, and we had an x value that was 1, 2, if I put my ruler on those, would they touch? So it's not a function, because that vertical line would go right through 2 points. So that would make it not a function. Does that make sense? That connection? Okay, if we graph them and they have the same x and 2 different y's, then when we draw a vertical line, it would go through 2 places. It would pass that relation in 2 places, and it would not be a function. It would just be a relation or a relationship. Okay. So, example 1. Let's clear the board and go to example 1. State the domain and range of each relation. Then use the vertical line test to determine whether the relation is a function. Okay, so A, does this have infinite solutions? Are the dots connected? No. The dots are not connected. So are there infinite solutions? No. Okay, so is this one going to be written as an inequality? No. Okay, it has to be lines. If the graph is a line, then we write it as an inequality. C. C would be written as an inequality, yes. Okay, so A, what is the domain for A? So maybe, what should we do first?
Count the squares.
Count the squares. Oh, no, that's helpful. What'd you say? Label the points. We could definitely label the points. Okay, so what's this one? 0, 0. Okay, what's this one?
0, 1.
Well, you have to.
1, 0.
Well, it wouldn't be 1, 0,
1,
because
1.
is that one 1, 1? Okay. My board is off.
2, 2.
Is it 5 and a half?
Before and half.
What would we? What we got? 4.5. So we have. Well, that one's not 1, 1 either.
No, it's like 1.5.
I was like, your guys' labeling here is not very great. I know on my board it's not very clear, but on your paper it's much clearer. So we've got 0, 0.
And then like 1 half.
So no, it goes to 1. Like it goes over. It's on the 1 line, but then it's between. So this would be 1 and then a half.
And then it'd be 2, 2.
2, 2.
That one is 2, 2. Okay.
Then
3
3 and
and 4.
4.5. Okay. Now the other side appears to be a mirror image.
Which is just negative.
Okay, so it's just -1, -1/2.
No, because the other one has to be positive, or else it would be in the other disjunct.
Very nice, Leah.
Or else it'd be in the
Other quadrant.
quadrant.
Yes. Okay, so what is this one then?
-1, +1.
-1, +1/2. Good. What's the next one?
-2, +2.
-2, +2. And the last one?
-3, +4.
Yes. Because if both of them were negative, then we'd be in the other different quadrant. Perfect. So what is... Do what?
But it's on the negative side, so why would it?
Because this is negative, left is negative, but up is positive.
Oh.
Negative left, and then negative again would be down here in this quadrant. Okay. All right, so what is our domain? The domain is the x value, yes. So we have a 0, right?
And 1.
We have a 1. We also have a -1, right?
Yeah.
So we could write we have a positive and a -1 if you want a little shorthand. Okay, we can write that because we have a +1 and a -1. A positive and a -2. We have a positive and a -3. Now, you don't have to do that. You could write 0, 1, 2, 3, -1, -2, -3. Just giving you a little bit of shorthand if you want it. Okay, so then what's my range equal to? The y, it's the y coordinates.
So would it be
It'd be negative.
1,
No, it'd be 1/2.
1/2, 2, and then 4.5?
0. Okay, so ideally you'd put it in the front, but we'll be okay. All right, very good. So then it says use the vertical line test to determine whether the relation is a function. So again, that's strictly like drawing some vertical lines. Switch colors. Oh my goodness. If I draw vertical lines, am I ever going to hit 2 points at the same time?
No.
No. So then is this a function?
Yes.
Yes. If it passes the vertical line test, it is a function. So I'm going to write in here in between. So we have a function. So remember, it's a relation and a function, right? Function is more specific. It's like, oh yeah, you're a relation, but you're also a function. Okay. B then. B, let's look there. What is its domain?
It's not a function.
Good, it's not a function. Yeah, it fails the vertical line test. I like it. So we can say not a function. I'll go ahead and put that at the top then. Because yes, right? It would fail the vertical line test right there. Good. All right. Yep, that's a great way to start. This one's a little bit easier even. So let's start down here.
It'll be 0,
-1, -2.
then 0, -1.
Okay.
And then 0, 1.
Nope, not 0, 1.
1,
1, 0.
0.
Mm-hmm.
And then
2, 1.
2, 1. And then 3,
3, 2.
Oh yeah, 3, 2, sorry.
Okay. And then let's go over to this side.
Negative 1, 3.
to calibrate my board. Okay, so since we have them labeled, what are the domain? Or what is the domain? Nope, we do not need -1 twice. Good catch. You can do like we did on the first one. Yep, you could have also just said that we had a positive and a -1, a positive and a -2, a positive and a -3, because we had those. And that would have been fine as well. A positive and a -2, okay. A positive and a -1. No, we have a +4, right? Okay, what do you guys think about that? We got -2, -1, 0, +1, +2. Oh, we have a +3. Right, we didn't get that one in there. +4, +5. Okay, and you already said this is not a function. Okay, good. Yes, sir. All right, so then let's look at C. How about C? So this one's a line, so what do we know we're going to have to do with it?
It's not a function.
Okay, well, it's not a function, you're right. It's going to fail that vertical line test, right? Because it crosses here all over the place. All over the place, so not a function. Okay, good. And what else do you know about the domain or the range? It has a mirror image. Yeah, this one's a little bit different though. Where's the mirror?
0, 0.
Yes, I guess maybe which axis? The x-axis, okay. Previously our mirror image was across the y-axis that we folded. This one's the x-axis. Very good. Okay, so, but what's different about this graph too? We talked about it when we started. It's going to be an inequality because it's all the points are connected. It has an infinite possibilities. Okay, so where are we going to start? What's our domain? Okay, so it starts at 0, right? Because this is our x-axis. Okay, and where does it go to? Where does it stop? Why nowhere? Okay, so that means it goes on forever. So any ideas how we're going to do that one? So we're going to have So we're going to have x such that x, that's how it's always going to start, is x such that for the domain, y such that for the range when we have an inequality. Okay? Yeah, man, that's it. X is greater than or equal to 0. The other one had a stopping and an endpoint. This one doesn't have, or it has a start and a stop. This one doesn't have a stop. It just has a start. So that's the only inequality we have. X is greater than or equal to 0. Starts at 0 and goes on. Perfect. How about the range then? Your y values. Where do your y values stop and start? Nowhere. Good. So what's your range? No, it doesn't. It has a range. What was it? All real numbers is correct. Okay. So your range is all real numbers. No, because it would be less than as well as greater than 0. Because we're going above, like we're including all of the numbers below 0 and all of the ones above 0. So it'd be all real numbers. Good question. Okay. So we're taking quite a little bit on just the beginning of notes here. Some background information, but we need to have it. So equations are often used to define the rule that determines the values of the range y associated with each domain x. Okay, so this is getting back into some stuff that we did last week in enrichment math as well. Okay, when we are given a relation, so we're given relation A here, it says our xy such that y equals x plus 2. They just gave us an equation. Okay, y equals x plus 2. And our x values, right, x equals 1, 2, 3, and 4. Make a table of ordered pairs to represent the relation, then graph the relation and state whether it is a function. They gave you all of the information in like shorthand, right, mathematical shorthand. And so that's going to be tremendously helpful because in here they're saying you're going to get your x and your y coordinates from this equation. That's why it's here. And you're going to be putting x in like 1, 2, 3, and 4 in for x. So that's on this table. That's all you're going to do. You're going to do 1, 2, 3, 4. You don't even need the last one. Then you're going to solve them here. Y is going to equal x plus 2. Well, x is 1. So what's 1 plus 2? 3. So my xy, my ordered pair is, no, it's an ordered pair. What's my x? 1. What's my y? That's my ordered pair that then I would graph. 1, 1, 2, 3. Okay, so for the next one, my x value is 2. I'm supposed to put in my x value there. So it's going to be 2 plus 2 is 4. So what's my ordered pair? 2, 4. Next, I plug in a 3. What's my equation? 3 plus 2, which equals 5. So what's my ordered pair? And my last number is 4. So what's my equation?
4 plus 2 equals 6, which would be 4, 6.
Which would be 4, 6. So then I graph it. So I'm going to go 2, 1, 2, 3, 4, 3, 5. Hold on. Nope. Went too far. And 4, 6. All right. Is that right? It's okay. And then state whether it's a function.
Yes.
Yes, it's a function. Okay, and these are often called function tables. Like when you create a table like that, it's a function table because you're going to put a number in and you're going to get another out. You might have heard them called in and out tables. It's not a very mathematical term, but it is one that they use with younger students. All right, so when no domain is stated, so if it doesn't say x equals 1, 2, 3, 4, okay, it is assumed to be the real numbers. Therefore, the graph would follow the established pattern already graphed and continue forever. And you are going to connect the points and make a line with arrows at both ends. Okay. Again, this is when no domain is stated, if it just gives you an equation. So if we look at B, they told us our equation equals 3, okay, or y equals 3. 1 is less than or equal to x, which is less than or equal to 5, and x is an element of the integers. Okay, so they gave us a domain. So how do you think we're going to fill this one out? What did it tell you your x values were?
Less than 1 and less than 5.
Less than 1 and less than, no, well, x, 1 is less than or equal to x, right? So it's saying x is between 1 and 5, right? X is between those numbers. So what number should we put in our chart? 1.
2, 3, 4, 5.
Yeah. And what does it say our equation is? All right, so y equals 3. So when x is 1, what's y? 3. When x is 2, what's y? Y equals 3. When x, am I supposed to plug an x into that equation? No. So when x is 2, what is y? 3. When x is 3, what is y? When x is 4, what is y? When x is 5, what is y? You got it. We don't have a 0. Well, but we don't have a 0 over here. So we wouldn't have any with 0 in them. It'd be 1, 3. Yeah, so this would be 1, 3. And 2, 3. And 3, 3. 4, 3. 5, 3. Okay, and so that's what you graph. So 1, 3, 2, 3, 3, 3, 4, 3, 5, 3. Is it a function? Yeah, passes a vertical line test. So yes, function. Good. Okay, so it does say, like, if this domain above, so if this domain here wasn't restricted, I don't know why my colors don't want to change today. My board is not calibrated well. Okay, and I just redid it. So if this wasn't restricted, the graph would contain all possible real values of x from 1 to 5, meaning it would be connected by a line. Okay, but it is restricted. So, because it says the restriction here is x is an element of the integers. So we can't use 4.6. Okay, it's restricted to just the integers, which are 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. All right, example 4 then. Let's look at it. It says graph D, so relation D, where xy, so you're going to graph it where it equals xy such that y is equal to plus or minus the square root of x, and x is 1, 4, and 9. So state the domain and range, and is this a function? All right, so I've got it set up a little bit for you to make it go faster. We've got 1, 4, and 9 for our x values. Our equation I've already pulled out, y equals plus or minus the square root of x. Okay, so how would we go about that one? Very carefully. Okay, so our y is going to equal plus or minus the square root of x. What's x? 1. So what is the square root of 1? What was it? 1. So plus or minus 1. So we're going to get 2 ordered pairs out of this. We're going to have 1, 1, and we would have 1, negative 1, because our y value is a positive 1 and a negative 1. Does that make sense how we're getting 2 out of there? Okay, so for the next one, our y is going to be plus or minus the square root of 4, which is what? 2. So plus or minus 2. So we'll have 4 positive 2 and 4 negative 2. And how about the last one? Plus or minus the square root of 9, which equals plus or minus 3. All right, then you're ready to graph those. Man, the seniors have lots of questions today. So 1, negative 1, 4, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, mine is a little bit of an estimate there because it's so hard to see the lines on the board up here. But then we need to state the domain and range, and is this a function?
No.
Okay, so we said this one is not a function. And what about domain and range?
No, we have to put that too.
Yep, so state the domain and range right here. So domain equals,
1, positive and negative 1.
is it positive and negative 1? No.
1, 4, and 9.
Domain is 1, 4, 9. Good. Range then is,
Is positive and negative 2.
how about let's start with positive and negative 1.
2 and 3.
And positive and negative 3. Good. Okay. Doing okay? All right. I was like, we're going to take up the whole hour today, especially with all of our interruptions. All right, then the last one. Since functions are a special type of relation, they are graphed using the same method. If the domain is not restricted, okay, and this one is an example where it's not restricted, because we just have f of x, so our function notation equals negative x squared. Does it say x equals this? No, so it's not restricted. Okay, if the domain is not restricted, you're going to, 1, draw a smooth curve connecting the ordered pairs. And you need at least 5 points. I don't care what 5 points you use. Now the thing with that is, you should always be, I gave you these 5 because it's good to include positives and negatives. Okay, so you get a good view of it. You want to make sure that they can fit on your graph. Okay, so generally it's keeping your numbers small. But also if you have fractions, like earlier on the one that had square roots, did you notice that each of the numbers was a perfect square? Like the numbers were 1, 4, and 9? Okay, you wouldn't want to pick 3 in there because you don't know the square root of 3. That would make your life harder. So if you have a fraction like 1/2 x, you would want to pick numbers that were even because you could take a half of 2. You can take a half of 4, half of 6. Okay, so sometimes looking at them and picking numbers, but we'll work on that a little bit more later. But I did give you these 5 numbers here, -2, -1, 0, 1, and 2. If nothing else, those are a good 5 to pick. Okay, so we're going to graph this function. F of x equals negative x squared. Then state the domain and range. So my work here is going to be negative. What's my x? No, it's not. No, it's not 2.
Negative 2.
-2. And then it's squared, right? It's negative x squared. I have to put the negative. Then I have to put my x in there, which happens to be another negative. Okay, and then I square it. So I'm going to keep my negative because I need to square my -2. What's -2 squared? 4. So now I have my answer, -4. So what is my ordered pair?
2, -4.
2, -2, -4. Perfect. All right. So with my next one, I have my x is -1.
So negative.
So I have -1 squared equals negative, yeah, 1. So my ordered pair is perfect. -0, yes, squared. Is there such a thing as -0? Just 0. Okay, so my ordered pair is perfect. Yep, equals -1. So I'm good. Equals -4. So what's my ordered pair?
2, -2. -4.
Okay, so then I'm ready to graph it. Okay, so negative.
Where's the middle?
So this would be your 0, 0, like this is the bottom 2 quadrants. So this is 3 and 4. Okay, so then we have -2, -4. I'm going to graph it on the paper, try to be a little more precise. -1, -1, 0, 0, 1, -1, and 2, -4. Okay, I got to pick these numbers, if you remember. I do not have any restrictions on my x values, so what should I do with these points? Connect them, yes, with that smooth curve, right? Okay, so I connect these with that smooth curve, which means, what should I put on their ends? Arrows, yes. Okay, I should put some arrows there. It is a function, perfect. So yes, we do have a function. Oh, you're right, it kind of looks like maybe it wouldn't. And then we're supposed to state our domain and range again. Okay, so this, hold on. In this case, we have the lines connected. So we should have some inequalities, right? So we can't, because we picked the numbers to put in there, but this is actually not our domain and range. It's not going to come from here. Okay, it's coming from our graph. So domain is my x or y values. X. So all across here, all across my x, where do they start and stop?
You don't stop.
Right, because they're going to keep going and they'll spread out this way, and they'll keep going and they'll spread out this way. So my domain is all real numbers is my domain. Okay, so I actually don't even need my brace here. So my domain is all the real numbers. How about my range? Does it include all the values that go up and down this y-axis? No, it does. Okay, so it does. So we are going to need braces there. And it's our y such that, because range is our y value. Where are our y values? They're here and down here, right? So what was this? No, this is down. Okay, they're less than or equal to what? 0. Perfect. Because yes, right there on that y-axis is 0. Good. Very, very nice. So do you guys understand the difference between like listing the domain and range versus using inequality? Sort of. Or having all real numbers. Okay. Okay. That's fair. It's true.